Chapter 2, Part 1 video, which will be 2.1 to 2.3. And you can read through the assessment statements, which means that these are the things covered on the IB exam. And you can look at the formula sheet to find the ones that would be pertinent to Chapter 2. And then here's the syllabus. Remember, number 6 is mandatory. So just to clarify some definitions, a basic definition for equation is where two expressions are equal. Pretty much meaning you must have an equal sign. If there's no equal sign, it's not an equation, it's a expression. So something like x minus 2 equals 5. That's considered an equation, whereas x minus 2 is an expression. Independent variable. So this is your input into a function. For most of you, you'll consider that the x value. Written in terms of. So if you have that statement here. So something like area equals pi r squared. Area is written in terms of r, the radius, which means that the radius is your independent, area is your dependent variable. That's your output. So you take your input, your r value, substitute it in, and you'll get your output, which is your a value. And in this case, so most of you will consider y or f of x your output. Domain is the possible input values. Range, possible output values, which we'll talk about in this section. Moving along, these are your 4 different ways that you can show a relation or a function, a graph, a table, ordered pairs, or a mapping. When you have a function, you have dependence on one quantity. So I'm going to give you this example down here. It says express the volume V of a cube as a function of the length E. So this would be your independent. This would, oh, sorry, just kidding. That would be your dependent. This would be your independent. So let's answer the question. The volume would be the side cubed. Part B says take what you have from part A, but instead I actually want it in terms of the surface area. Well, first I'd have to figure out what the surface area is. Surface area would be the 6 faces that all have the same area. The area of each face is e squared. So to get the volume in terms of surface area, you'll notice that the relationship between the two is the independent variable. So I'm going to solve for that. S over 6 is equal to e squared. E is equal to the plus or minus square root of s over 6. But since we are talking about a real-life problem, there's no possible way for the length of the cube to be negative, so I'm only going to use the positive. So I'm going to come back over and find that the volume is equal to the root of 5, oh, sorry, not 5, s, surface area, over 6, whole thing cubed. And just to make it look a little nicer, I'd rather write it as the surface area divided by 6 to the 3/2 power. So that is the function of volume in reference to or in terms of surface area. Moving on, find the domain of each. So in this case, the domain would just be the x values that are shown. Letter B, the domain says that we look at the independent, which is r, and say what values of r would be possible. There's no such thing as having the radius of a circle equal 0 or be negative, so the radius has to be greater than 0. For letter C, we know that the denominator of a fraction can never equal 0, therefore there's my domain. And then letter D, we know that the square root can only take positive values, so my x has to be greater than, and yes, it can be equal to 0. Remember that the square root of 0 is 0, which is why I can put the equal sign. Now, the other thing I probably want to include, using the notation from the first chapter, would be that r is greater than 0 where r is in the real numbers. X is not equal to 0, but x is also in the real numbers. And here, x is greater than 0 where x is in the real number. So I can actually use real number values for any of those domains. Function is a relation in which no two different ordered pairs have the same first coordinate. So for a function, each x value has at most one y value. Vertical line test is usually the way that you guys know if a relation is a function or not. Example 3, what is the domain and range for the function y equals x squared? So domain, we would be looking at what numbers can you square in real life. Well, I can square a negative number, a positive number. I can square 0. I can square a fraction, a decimal. So in this case, the domain is x's in the real numbers with no restriction whatsoever. Your range. If I square a number, what are the type of numbers that I can't get? You should realize that when you square numbers, you never get negative values. So y would have to be greater than or equal to 0 because we can't get a negative value when you square, where y is in the real numbers. Notation, I just wanted to have you notice this weird backwards bracket is your exclusive bracket in the book. So what I mean by that is usually if you want to go 5 to 6 but not including, we use the rounded brackets. Your textbook actually does this instead, which looks very odd to most people. So if you look here, this is your inclusive, so includes 0. Here is exclusive, does not include infinity. We never ever include infinity. The other notation thing I wanted to mention, notice function notation, which you're probably used to. This is mapping notation, which is essentially saying the exact same thing. It says the function's name is f, and the f takes the x and maps the x value over to the x squared. So it's exactly the same thing as function notation. You have to know that notation. It does show up here and there. So finding the domain of this function, I picked this function purposely because it has 2 domain issues. The easier of the domain issues is the fact that it's a fraction. So the first domain issue is the fraction. And fractions, the problem is that the denominator should never equal 0. So I'm actually going to solve this equal to 0. So I get 9 is equal to x squared, and x is equal to plus or minus 3 because I'm taking the plus or minus square root. So I'm going to actually come over here and map out my domain. So I have negative 3, positive 3. I can't equal those values. Second problem is the fact that it's a square root. So all even roots have a restriction. The restriction is that the value underneath, so the value underneath would be 9 minus x squared, has to be greater than or equal to 0. So what I'm going to do is come over to my sign line that I already started, and if I put in the value 0 into 9 minus x squared, I would actually get a positive value. If I put in positive 100, which would be somewhere down this side of the line, I would get a negative value if I put in 9 minus 100 squared, and same thing over here, 9 minus 100, negative 100 squared. So when you look at the domain actually for this function would only be here. The reason why, at negative 3 and positive 3, the square root value would have been 0, and we have an issue with that being a fraction. Secondly, if I put in any value between negative 3 and 3, I am guaranteed that the square root of 9 minus x squared will be bigger than 0. So in this problem, there's our domain. In terms of the range, for this problem, I'm actually not going to do this one because your textbook just uses the calculator to recognize the range. Actually, for both, I think it's important to be able to do this type of problem for domain, not as much for range. But for any domain problem, you really should be using a sign line to check what values work and which ones don't. The reason I use a sign line is because of the square root. Square root functions will only take positive values. Moving on. So we are now in 2.2, composition of functions. So notation-wise, you have 2 different notations. The way that we would say it, g of h of x. The better known notation is g of h of x. So this is g's input, whereas this is h's input. Okay? The domain of a composite function is the set of all x in the domain of h such that h of x is in the domain. So when we start talking about domain problems, it will be a little bit tricky. So if the domain of h is x, then I would take that x value, input it into h, and I would get the h of x value. Now, the h of x value becomes the domain for g of x. So once I put that value into the g function, it's got to work again. So it's kind of a twofold domain. So example 8, so this is a mapping, and I'm going to rewrite the mapping. So f of x is equal to 3x minus 6 is what this part says. And given that g of x is equal to 1/3 x plus 2, find the following. Just to make sure I'm only going to do part A, f of g of x. I like always rewriting it into the other notation because this tells me that this is my input. So I'm going to take my f function, which is 3x minus 6. I'm going to take my x and replace it with the g function. So I get g is 1/3 x plus 2, and then minus 6. So I'm going to distribute and get x plus 6 minus 6. Therefore, I get x. Moving on. Example 9 asks you to, given a composite function, find two components of f and g. And there's actually multiple answers to these problems, but I'm going to do the ones that are probably the most noticeable. So if this is h of x, then there's a f of x and a g of x that could be composed to make h of x. So what I usually do is try to find kind of like an inside function. If you think about calculus, we talk about inside functions a lot. So if I make f of x and I make g of x, this is kind of like the inside function, and this is kind of like the outside function, if you have any idea what I'm talking about. The inside function, I'm going to call it x plus 3. Okay? Then I'm going to replace the x plus 3 with just an x. And then we're going to double check our answer. So f of g of x, f of g of x. What does that say? Take the f function, which is 1 over x, and instead of writing x, I'm going to put the g in there. And you want to double check that you got exactly the same thing that we started with. So this would be considered a component function, the two component functions. You can definitely do them for these. So this inside would be my g. This inside would be my g function. So the g function I consider my inside function. Finding the domain of a composite function. So you just want to make sure that x has to be in the domain of h, and then that h of x is in the domain of g. So if you go back to originally the picture that we had, I'm not going to draw it again, there's a twofold domain problem when you do composites. So let's look at g of x and h of x are given. So letter A says find g of h of x. So you'll notice I always write this notation. So in the g function, x squared minus 4, I'm going to substitute in my root of x. And what you'll notice is the root of x squared simplifies and gives me x minus 4. So if I just gave you this function, you would probably tell me that the domain is all real numbers. I can take any number and subtract 4 from it. But in this problem, you have to think about two things. You got to think about the root of x. That's where the domain starts from. Okay? The domain for root of x actually would be that x has to be greater than or equal to 0. After I take that value, I'm going to square it, and I'm going to subtract 4 from it. There's no problem squaring a value, so this will be the domain for part A. So the actual answer for the domain is x is greater than or equal to 0, even though if I just looked at the result of the function, x minus 4, it looks as though the domain is x is all real numbers, and it is not. And let's go the other way, just to make sure. H of g of x, that would be, well, what am I taking? H function, which is the root, and inside the root, I'm going to put the g function, which is x squared minus 4. So I'm going to first look at the x squared minus 4 and check, is there any problem with the domain? Meaning, is there any x value that can't get squared? And so far, my domain would be all real numbers. Now, I'm going to take that squared number minus 4, and I want to look at, is there now an x value which would cause me not to be able to take the square root? Well, in this case, yes, there will be. Come over here. So now I'm going to really look at the full domain of this function, which says that I can only pick numbers for x squared minus 4 that will be bigger than or equal to 0. So what I'm going to do is solve it equal to 0, which would mean x equals plus or minus 2. And then I'm going to do a nice little sign line here, a straight one. I'm going to put negative 2 here, positive 2 here. I can take the square root of 0. What that means is if I put in positive or negative 2, I can take the square root of negative 2 squared minus 4. That would just give me 0. Then I'm going to test the value. I'm going to test 0. If I put in 0, it becomes negative. If I put in any of the values outside of negative 2 to 2, they'll be positive. So here's my domain for this function. My domain written, I'm going to use the notation that you just saw a second ago, is negative infinity to negative 2 inclusive, union with 2 to positive infinity, not inclusive. Crazy looking notation, right? All right, moving on. So inverse functions. I think I can squeeze this one in also to this video. So we'll try to do this quickly. Definition of an inverse function, pretty much you're undoing a function. So the major thing that I want you to know is if you do the composition of the two functions that you think are inverses, you should end up with x both times. This is an and, not just one, not the other. It must be both ways. Okay? So given the linear function and its inverse, verify the result by showing. So this is what you'd have to show. It's a two-part process. Part 1, you have to show that f of f inverse of x equals x. You have to show that. And the 2-part would be that you take the inverse first, composition with the function of x, and you want to show that that equals x. So how do we show? We actually do the composition. So f of x is on the outside, so 4x minus 8. In this case, I want to put in the inverse function. Oh, lordy, I missed a step. I'm going to put it down here. First step actually is part A, is to find the inverse. So to find an inverse, you take the function, which I'm going to write with y equals, switch the x and y, and then solve for y. So y would equal x plus 8 over 4. Okay? So to find inverse, switch x and y, and solve for y. Sorry about that. Now we can use the answer that we just got down here to come up and put this is my inverse function. So I'm going to place that right here. X plus 8 over 4. And then I'm going to simplify. So I get left with x, so this one works. We're going to come over here and use the inverse function, which is x. Oopsie. X plus 8 divided by 4. X, the function that you're inputting is f of x. There it is. And we get 4x over 4, which equals x again. So because both of them work, they are inverses of each other. Graphically, an inverse is always going to be a reflection across the line y equal to x. What it does is point by point, any point a, b that's on f of x will transform over to the inverse function by switching its x and y value. Okay? Find the inverse of the function, so we know how to do that. I'm going to use the function y is equal to x squared plus 2, switch the x and y. And we're going to solve for y. And then when I take the square root, I need the plus or minus square root of x minus 2. This is extremely important. It says that I'm going to find the inverse of this function. If you just mentally really quickly think about it, it would look something like, and it won't be perfect, that. What you'll notice is that the inverse is not a function, which is why I have these here. It makes it not a function. It's actually a relation. So next thing I'm going to look at is the fact that we want to talk about one-to-one functions. So one-to-one functions. A function is anytime it passes the vertical line test. So that's this guy. I cross through that blue parabola only once each time. One-to-one function passes both the vertical and horizontal line test. So here you'll see that the red line, which is now yellow, represents the fact that this does not pass through the horizontal line test. What that means for us is that the inverse will not be a function. So what we do is we chop off the function. We just essentially create this new domain. So in this case, we do a domain where x is greater than or equal to 0, and we say we're only going to look at that because now my inverse will be a function because the original function is one-to-one. So that is the definition that you have there. Example 13 says, given that g of x is x squared plus 2, such that x is greater than or equal to 0, find g inverse and state its domain. So if we have that x is greater than or equal to 0, and I'm going to just do a nice little graph of that again. What we originally had was there. I'm going to make it greater than or equal to 0, so it would only be the right half of the graph. Y is equal to x squared plus 2. Switch the x and y's. Subtract 2. And square root. So we do plus or minus square root of x minus 2 equals y. Well, if your x is greater than or equal to 0, then you want to look at the fact that if x is greater than or equal to 0, my y values are greater than or equal to 2. How do I know that? There's two different ways. The graph above shows it. And secondly, think about the values that you would put into x squared plus 2. If I put 0 in, I get 2. If I put 1, I'm going to start getting values bigger than 2. That's how I figured this out. This becomes the actual domain for this problem. Now, what do I mean by that? Because we end up with where x is greater than or equal to 2, and I'm taking that from y equal to, why does this happen? It's because inverses switch their x's and y values. This is going to be my new domain for x. What this also says is I'm not going to need the plus or minus. I'm only going to need the positive because I'm using the positive x values. Therefore, I only want positive y values. I'm actually going to draw in a quick sketch of the inverse. So that's 0, 2. Well, now that point will become 2, 0. And that's what the inverse graph looks like. The domain is where x is greater than or equal to 2. And again, remember, I use the range from the original to create the domain for the inverse. There's another one where now the x is less than or equal to 1. Or sorry, negative 1. So 1, 2. So that would be the graph for that function. So if x is less than or equal to negative 1, the domain for the g function, I should actually write g function, the range would be that the g values must be greater than or equal to 3. What that tells me is that this is now the domain for the inverse function. But we need to find g inverse. To find g inverse, I switch the x and y's. Same exact problem we had a second ago. X is equal to square root of y minus 2. And so this is my inverse function now. And I'm going to write, and when I write my inverse function, you notice I got to rewrite the x value. So my g inverse of x is equal to the square root of x minus 2, and the domain now will become x is greater than or equal to 3. And if you're curious to what that looks like, This point was -1, comma 3. So now I'm going to do 1, 2, 3, -1. And there's the point. And if I want to make this work, that's what it would look like. So that should be, there's a little summary of finding the inverse of a function. If you need the summary, essentially we did pretty much everything. I think example 15 becomes a little bit repetitive based on what we've already done. And we can consider the function. We should be able to find G inverse. And we should be able to solve that equation, making sure that we understand the composition function. Remember that this is F's input. And let's see, think that would have been the last part. So what I will do is at least do this problem just because it looks like I have a little bit of time left. So the F function is 2. Oh, actually, there's a little bit more to this. I did not find the inverse. So let's start with finding G inverse. So this is what I'm going to be looking for. So I'm going to switch my x and y's. I get 3x equals 1 minus y. I'm going to bring y to this side. I'm going to bring 3x to the right side. There's my y function, which is G inverse. Which makes me think, did I make a little mistake before with that x? I'm going to go back. And I just wanted to make sure. I believe I never switched my x and y's. That is the problem. Sorry about that, guys. All right, so now that I have that, I can do part B, which would be, in this case, let's see. Part B says f of G inverse of x equals 2. So the f function is 2x plus 4 and equals 2. The x value that I'm going to put in would be the G inverse, which is here, which would be 1 minus 3x. And so we end up with 2 times -3x plus 4 equals 2. I'm going to divide by 2. I'm going to subtract 4. And I'm going to divide by -3. There's my x value. So I believe that's part 1 done for you. So you should look through and see what parts were confusing. If any parts were confusing, you probably want to go back and do a few little homework problems from that set.